Good morning to everyone. This is Mahesh Chandra. Today I am presenting my internship project titled EV ADAS system, that is real-time EV dashboard and ADAS warning system using STM32, Blue Pill and Pixim Lab. During this internship, I learned automotive embedded system concepts, advanced driver assistance systems ADAS, and developed a simulated EV safety monitoring system using STM32 and Pixim Lab. This presentation covers my complete learning journey over 16 days. On coming to the day 2, I learned how to set up the STM32 development environment using STM32 Cube IDE and Cube MX. I configured GPIO pins for LED control, understood STM32 Hall functions such as Hall GPIO written pin and Hall GPIO toggle pin, flashed the firmware using ST-Link and simulated the hardware in Pixim Lab. This day helped me understand the basic workflow of STM32 programming. And on coming to the day 3, I worked with the analog to digital converter. I configured ADCC channels to read accelerator, brake, battery SOC, and motor temperature values. And I learned how analog voltages are converted into digital values and displayed the sensor readings with through the UART communication. This was the foundation for collecting real-time vehicle data. And coming to the day 4. On day 4, I interfaced the HCSR04 ultrasonic sensor with STM32. I used timers for microsecond measurements and calculated obstacle distance using echo pulse duration. Three ultrasonic sensors were connected to detect obstacles from the front, left, and right sides, which forms the basis of the ADAS system. And coming to the day 5. On day 5, I learned STM32 timers, interrupts, and cooperative scheduling. Different timers were configured for the EV control loop, ultrasonic sensor scheduling, motor PWM, that is pulse width modulation, and buzzer generation. And I also understood the interrupt service routines ISR and how embedded systems execute multiple tasks efficiently without an RTOS. And coming to the day 6. On day 6, I implemented the EV controller module and the system calculates the vehicle speed, battery state of charge, power consumption, torque, and driving range. And I also implemented Eco, Normal, and Sport driving modes. These three are the three modes in this project, along with the regenerative braking, which improves the battery efficiency during braking. And coming to the day 7, on day 7, I designed the vehicle state machine with 5 operating states with parked, ready, driving, regenerative braking, and fault. Different fault conditions like low battery, over temperature, collision risk, and sensor failure were monitored. Critical faults immediately stopped the motor and generated the warning alarms to the electric vehicle. And coming to the day 8, on day 8, I developed the ADAS engine using ultrasonic sensor data and vehicle speed. The system calculates time to collision and generates collision warnings. Blind spot detection and parking assistance were also implemented in this project. Alarm hysteresis was used to avoid unnecessary repeated warnings. And now coming to the day 9. On day 9, I implemented UART communication, that is universal asynchronous receiver and transmitter communication between STM32 and the external dashboard. Vehicle parameters like speed, battery SOC, torque, power, and obstacle distance were transmitted using a structured packet format. I also implemented a command shell to change driving modes, inject faults, and monitor the system. And coming to the day 10, on day 10, all modules developed during previous days were integrated into a single application. I tested sensor accuracy, regenerative braking, drive modes, watchdog timers and their operations, and timing performance. The objective was to verify that all components work together reliably. And coming to the day 11, on day 11, I developed a Python based dashboard. It displays the vehicle speed, battery SOC, power consumption, motor temperature, torque, and driving mode in real time for the electric vehicle. UART packets from STM32 were decoded and visualized using Python libraries, creating an interactive EV dashboard, that is, electric vehicle dashboard. And coming to day 12, on day 12, I extended the dashboard by adding a bird's eye view of the vehicle. The dashboard displays obstacle positions, collision warnings, blind spot indicators, and fault notifications with different colors. This gives the driver a clean and clear understanding of the surroundings. And coming to day 13, on day 13, I executed all functional test cases and documented the results, and different scenarios like collision detection and fault recovery and sensor timeout and alarm hysteresis were verified. A complete test report was prepared, ensuring the system met the required specifications. And on coming to the day 14, on day 14, I finalized the project documentation, source code, configuration files, Python dashboard, test report, and a demonstration video. The complete project was reviewed and prepared for final submission with proper modular coding and documentation. And for this project, electric vehicle dashboard, this project successfully demonstrates an embedded automotive ADAS system using STM32. Throughout the internship, I gained practical experience in embedded C programming, STM32 peripherals, UART communication, timers, interrupts, sensor interfacing, fault management, and automotive software development, and all. This internship significantly strengthened my embedded systems knowledge. And I want to conclude that this internship gave me practical exposure to automotive embedded systems and ADAS technologies. I learned how different software modules integrate to build a complete embedded application. In the future, this project can be extended by integrating CAN communication protocol into this EV dashboard and real hardware implementation, camera based object detection, and AI based driver assistance. Thank you for your valuable time. And my project was visualized on the display.